everybody. This video is going to be about gas stoichiometry, which I know we all hate because stoichiometry is tedious. But it's not too bad if you remember stoichiometry. So to start out, there's this cool thing called standard molar gas. Or standard molar volume. Whoa, off to a great start here. Volume. And so what that is at STP, which is standard temperature and pressure, which is very important, 1 mole of an ideal gas occupies 22.4 liters. Basically means 1 mole equals 22.4 liters. Which is a conversion that is going to be necessary for these problems. But it has to be at standard temperature and pressure, which, just remember, that means temperature equals 273 Kelvin or 0 degrees Celsius, and pressure equals 1 atmosphere or any of the variations of that. So I thought, just to review stoichiometry whilst using this, we do a limiting reactant example just to refresh our memories. So let's do that. So say we have 8.55 liters of ammonia. Ammonia reacts with 4.90 liters of oxygen. Remember, oxygen's a Bringelhoff at STP. So what is the limiting? What is the excess? So the first thing, if you remember for stoichiometry, is you have to write the balanced equation. So we have ammonia plus oxygen gas, which is going to create NO and H2O. I think we're looking for the amount of, let's just say we're looking for the amount of nitrogen monoxide produced. So first we have to balance this. And I know because I've already done this, that's 4, that's 5, 4, and this is a 6. So 4, 5, 4, 6. So since you don't know which one's limiting and which one's excess, you have to work the problem twice. So let's start with our ammonia and let's work to nitrogen monoxide. And since the problem didn't tell us we could work to either one, but if the problem tells you, make sure you work to the right thingamabob compound. Okay, let's start with ammonia. So we have 8.55 liters of ammonia. And because we know it's at STP, we can use our new conversion. So that'd be 22.4 liters of ammonia equals 1 mole of ammonia. And then we have to do our molar ratio. And since we're going to nitrogen monoxide, that'd be 4 to 4. Not a lot of space today, but that nitrogen would go on top. Let's go on the bottom. These would cancel and just be 1s. And then we want it back in liters. So we're just going to say 1 mole nitrogen equals 22.4 liters. And that gives us, wow. Oh, okay. So when you do this problem, as we know, our units all cancel out so nicely. We're left with liters of nitrogen monoxide. But you also see that this in the top, or this is in the bottom, this is the top. If you wrote it out in a line, you'd see that they cancel also. So you're just left with 8.5. So you don't have to even put that in the calculator. That gives you 8.5 liters of nitrogen. Now, we don't know that's our answer because we have another product. So we have to work it again. So do the same thing, but this time with oxygen still convert liters to moles. Same number no matter what. It's like similar to Avogadro's number where it didn't change. Now this time you have to put the molar ratio. So since there's a 5 in front of the oxygen, 4 in front of nitrogen monoxide, and then just have to convert that back to moles, or back to liters. And that will give you 3.92 liters of NO. Now, since this is the smaller amount, remember this is the actual answer, and that means oxygen is the limiting reactant, and ammonia is the excess reactant. So now if it asks you how much of your excess is left, what you need to do is you either need to, this is our theoretical yield, either using the theoretical yield or the limiting reactant, you need to work backwards. So I'll start with our yield. We have liters of nitrogen. You're just going to work the same thing again and just go back to ammonia, which it all cancels out because we know the molar ratio is 1 to 1. So that gives us 3.92 liters of ammonia that was used. So if we want to know left, we take the original amount minus the used amount. So that would give us 4.63 liters of ammonia left. Woo! Oh, I made the screen tiny. Go back, please. Whoops. Sorry, y'all. Well, left. Whoop. Okay. I can't get it to go back. Ow. Okay, that's okay. We'll work with the tiny screen. Okay. So that's how you use that conversion. And just make sure when you use the 22.4, you're at standard temperature and pressure. If you're not, you basically work it the same as if it was at that standard pressure, and then you're going to convert as if it's easier if I do an example. So we're looking for how many milligrams of oxygen are needed to react 28.0 grams of an ammonia again at 24 degrees Celsius and 0.950 atmospheres. So this is the same equation from before, so I'm not going to rewrite it. Now we're just going to do as if it was normal, but now we have grams, so we have to start by converting our ammonia into moles by using the molar mass. Whoops. So now we have moles. So now we can convert from moles to, well, now we're going to do the molar ratio. Don't have to convert to liters yet. So we're looking for oxygen. So we know 5 moles of oxygen over 4 moles of ammonia. And then we want liters of oxygen. So that would be 1 mole of oxygen over 22.4 because we're pretending it is at STP right now. But we're looking for milliliters, so then we're going to have 1,000 on the top and 1 liter on the bottom. So let's see. Nothing cancels out, so you're going to have to put 28 times 5 times 22.4 times 1,000 divided by 17.04 times 4. So that will give you 46,009.4 milliliters of oxygen. So that is, now we're going to use the combined gas law, because this is your V1, because our T1 equaled standard temperature and our P1 equaled standard pressure, because we pretended that's what it was at. And if we go back to the equation, this is now our T2, and this is now our P2. So if you do the algebra, solve the equation, you get V2 equals V1 P1 T2 over P2 T1. So now you just plug all the numbers in. So you plug that amount in milliliters we found from the stoichiometry times the atmosphere. You can move it over a little. Go, go, go. Times the atmosphere times the original temperature in Kelvin, 297, over the pressure from the problem times our standard pressure. And once we do that math, we get that the actual volume is 27,000 milliliters of O2. So that's how you do it when it's not at standard pressure temperature. So yeah, stoichiometry is not too bad. Just have to remember all the little nuanced stuff. So hope that helped. Good luck on your test.